Doncs bon dia, benvinguts a l'Escola de Camins i a la Universitat Politècnica de Catalunya. Us dono la benvinguda en nom del director de l'escola i de la universitat, com acabo de dir. El director està en un congrés i hauria vingut, però y per tant, doncs he vingut jo. Muchas gracias por venir. Está muy bien que tengamos esta sala llena. Esto sin duda significa que el tema de transporte de sedimentos y morfología fluvial tiene interés y, por supuesto, que tenemos un gran conferenciante, profesor Parker, y por tanto ambas cosas coinciden y esto provoca que efectivamente pues hayamos venido. Naturalmente esto sí, siempre ha ayudado porque hagas una buena promoción, ¿no? Pero esto es como secundario. Bueno, pues gracias al profesor Juan Pedro Martín Vide por organizar este evento y, por supuesto, gracias al profesor Gary Parker. Thank you, Professor Gary Parker, for accepting the invitation to give this lecture. El profesor Parker es un investigador y profesor del Departamento de Civil and Environmental Engineering de Illinois y, bueno, ahora lo va a presentar el profesor Juan Pedro Martín Vide. Bueno, esto trata, ahora estaba mirando, digo, esto trata de morfología fluvial y tal, entonces no es nuestro delta, pero si le damos la vuelta a esto, entonces ya se parece mucho más al del Llobregat, ¿no? Por la orientación.
Hola, buen día a tothom, buenos días a todos. He preparado unas pocas palabras de presentación, 3 minutos para presentar a Gary Parker en inglés, en mi inglés regular. Good morning to everybody. Thank you for your interest in being here today, to all of you. My duty today is to briefly introduce Professor Gary Parker. For those of you who are familiar with the literature of sediment transport, river mechanics and alluvial problems in fluvial and coastal zones, yes, he is the Parker in the Parker formula for the transport of mixtures. He is the writer of the chapter on core sediment transport in the ASCE Sedimentation Engineering Manual. Yes, he is the author of a book on meandering channels. He is the researcher that introduced a rational method of hydraulic geometry in gravel beds, the one who linked bankfull flow to the threshold of sediment transport, the one who corrected the well-known Meyer-Petter and Mueller equation, the researcher of turbidity currents and submarine phenomena in the continental shelf, and so on and on and on. I was about to forget the excellent electronic book you can use through the web page you have in your hands. In the brochure in your hands, there is the web page where you can get into and look at his excellent electronic book. If you read his work, you will always recognize his clear, clever contribution to the knowledge. And I would say that it's always knowledge what he is in search of, but not power. In this short praise of Professor Gary Parker, I would like to make a second point, the final point. Science has its own sociology, as in the diffusion of knowledge, the exchange and discussion of ideas, the motivation of young scientists, the teaching, and so on and on. I first met Gary Parker in a conference, the right place for exchange and diffusion. I can tell you that anyone there in these conferences feels how much Gary is willing to help, to give generously ideas, references, paths to follow in research, especially to young people. You must know today that Gary is here because he enthusiastically helped a young PhD of UPC, this university, who is in the room, by the way. He went to him with a question, and now is the result. He's giving this lecture today here, thanks to this question. Greeks, the Greek people, Greeks, ancient Greeks, had the word ethos, today ethics, for what I feel is the role of Gary Parker in the sciences as a social thing. Finally, he used to be l'enfant terrible, Gary. Now he's also il maestro. And then I would like Maestro Gary to go ahead and give us the lecture. Thank you very much.
Thank you very much for this introduction, and then we go with the lecture.
I first give my great thanks to Juan Pedro, first for inviting me, second for giving me an opportunity to work with his student Carlos Ferre, who came to visit me and my colleagues at the University of Illinois and was able to conduct a major piece of research there that I think both Juan Pedro and I are very proud of. I appreciate your very, very kind and unnecessarily extravagant introduction. But we have a word in English, beggars can't be choosers. If you beg for something, you can't say, no, not this, that. So I take it very much. I have had a long association with Juan Pedro Martin Vide through research and through interaction with other researchers that has proved very valuable to me. This is my third visit, my fifth visit to Barcelona, but my third visit specifically to interact with you in regard to this university. I also would like to thank Alain Bateman Pinzon, who has been a collaborator with me also for many, many years. We have had wonderful conversations both with each other and with our various students and postdoctoral researchers. That is of great benefit to me. I am not actually sure, but I imagine the person in the audience I may have known longer than anybody else is Albert Falke. Falke is here. I think we first met sometime in the 80s at a Euromec conference. Early 90s. Okay. So, okay, early 90s. I'm an old man and you're an old man, so we don't remember very well. It was a long time ago. And I also appreciate my interaction. I have a very strong interest in coastal research, which I have not fulfilled, but Albert is one person to help me consider to move more in that area. I should also mention that I am only going to talk about half of the kind of work I do. The other half is in the deep sea, and I have to tell you with great pride that in 2003, when the River Coastal and Estuarine Morphodynamics Conference was held here, there was also a major conference the week after at the Institute of Marine Sciences here in Barcelona. And it seems I may have been the only person to attend both conferences because the worlds are somewhat different. Okay, my talk is a general one. It is broad but not deep. My goal for the talk is not to impress you with fascinating new research results, but to bring a more general audience into some kind of an appreciation for the kind of things that we do when we work on research, both basic and applied, in regard to rivers. Also, in this talk, I'm going to emphasize applied aspects, but I should point out that each application I show has also strongly interacted with basic research. And finally, I want to mention that of the things that I show, I have always been a small player. I have students, postdoctoral researchers, and colleagues from around the world. So if you say it, don't say Gary Parker did this, you say Gary Parker did a small part of this. So I begin. So we'll look at some examples of sediment transport and river morphology. The deltas we see here are the Wax Lake and Atchafalaya Delta of a branch of the Mississippi River, and this will also be one of the topics that I will discuss today. Now, there may be a number of people here who are quite familiar with river hydraulics or quite familiar with water quality management, but may not be so familiar with sediment transport. So I show you a video from my colleague Mark Schmeeckley at Arizona State University that shows a mechanism of sediment transport known as, that shows a mechanism of sediment transport known as bed load transport, where the particles move close to the bed, sliding or rolling or saltating. Above the coarser particles, you can see some particles that are moving in suspended load, where turbulence can carry them high up in the flow. This is to illustrate bed load transport, which we will be talking about a lot in this lecture. This illustrates suspended transport. What I show you is not a fluvial flow. It's actually a turbidity current, a model of a deep sea sediment transport event. But it is dominated by suspended sediment. You will see the front of the turbidity current moving through. There is also bed load transport, but you see from the pixels here that the great majority of the load is in suspension, moving much higher in the water column. So these are two basic modes of sediment transport that we will consider. They are not completely distinct. There is not a sharp line, but nevertheless it's useful to divide them into that part of the load which travels close to the bed and that which can ride much higher in the flow. Now, this gives you a feel for the phenomenon of sediment transport, but we always have the question, what we see in the laboratory, does it really connect to the field? And only recently we have developed the kind of technology that allows us to see this. It only works in rivers where the suspended load is not too high, but I'm going to show you an example of a recent observation of bed load transport directly in the field on the Trinity River in California. And I got this video from Andreas Kraus, who is working on river restoration on the river. So this is a camera placed on the bed. There is both bed load and suspended load transport. The largest gravel there is probably on the order of about 100 millimeters. The suspended transport is not too high, otherwise you would not see anything, but it is also there. So I hope this gives you an appreciation of what we are looking at. In sediment transport, we wish to calculate how much sediment is moving, what is the grain size distribution of what moves, and how it responds to the flow. In morphodynamics, we use information about fluid mechanics and sediment transport to calculate how the bed of a river or the coastline or a submarine fan interacts with the flow to create morphological structure. I begin with the concept of bankfull discharge. My talk today concentrates on alluvial rivers, rivers with a bed and floodplain of sediment. Not all rivers are alluvial rivers. In Catalonia, we will also find many bedrock rivers, and they are of great interest to me and a topic of my work also, but I will not discuss them today. The characteristic feature of alluvial rivers is they have a floodplain that has co-evolved with the channel. And such streams usually have a definable bankfull discharge, which, I'm colorblind, I don't see it so well, which can usually be defined in terms of a plot of water surface elevation versus discharge. When the flow is within the channel, we have a steep rise of water surface elevation with discharge, but at some point, as we spread onto the floodplain, increasing discharge does not raise water surface so much. And we can use that to define a bankfull discharge, and we have taken that as a simple measure of the type of flows that have created the channel and floodplain itself. The particular image I am showing you here is of the Wabash River in Illinois as it flows into the Ohio River, and the flow in this image is a little bit above bankfull. Now, we need a few concepts in order to express the ideas of this lecture. We need to discuss bankfull width and depth. They are approximate ideas, but I believe useful ideas. The example I am showing you here is from a river in Papua New Guinea, a country on an island, New Guinea, north of Australia, where I and my colleague Bill Dietrich worked for about 15 years. And this particular reach of the river has a very wide floodplain. The river has natural levees. It's on the order of about 200 meters wide. It actively migrates across the floodplain. And this shows one sample of many cross sections where we can see both the bed of the river, the floodplain, and also natural levees built on the river. You can see that the river is on the order of about 200 meters wide and on the order of about 10 meters deep. This is an approximate measure of bankfull width when we would start to spill significantly on the floodplain. Obviously, it will be measured in terms of the lower levee. And an equivalent rectangular cross-section with the same area gives us our bankfull depth. We need a few parameters for the lecture. So I am using QBF for bankfull discharge, bankfull width, bankfull depth. I will also need a slope, downstream slope, a characteristic surface grain size, and acceleration of gravity. Don't laugh, because there are also rivers on Titan today where the fluid is liquid methane and the sediment is ice particles, and so gravitation acceleration is different, and the specific gravity of the sediment is different. I use a submerged specific gravity, which is about 2.65 minus 1 according to our friend Archimedes, or 1.65 for quartz. On Titan, the value of R is about 1 instead of 1.65, and the value of G is only about 1/7 of the value on Earth. You may not be interested in river engineering on Titan, but I like the example. And then, of course, the kinematic viscosity of water. It would be methane on Titan. From this, we can form a number of dimensionless parameters, but there are two that I will use consistently in this lecture. One is a bankfull Shields sediment mobility number. This actually is only an approximate expression, but it nevertheless captures the basic idea. The Shields number involves the bankfull depth of the channel times the slope divided by submerged specific gravity divided by grain size, which means a deeper and a steeper flow is more able to move sediment. When the sediment is heavier or larger, it's more difficult to move. And then we have below that a dimensionless grain size, which we may not need on Earth if we're always using quartz, standard Earth gravitation, and kinematic viscosity. But when we are working on, for example, Mars, where there were rivers, and Titan, where there are rivers, we would need to change those values. Now, there is a very standard diagram in sediment transport that some of you will be familiar with. I am giving it in a form that plots bankfull Shields number versus dimensionless grain size and asks whether sediment, a characteristic bed size, would move at a bankfull Shields number. And we have a regime below the first line of no motion. We have a regime above that first line in which sediment moves, but mostly as bedload transport. As we start to approach the top line, suspended sediment becomes more significant, and above the line, suspended load becomes the dominant mode of transport. So these are the three standard regimes. Again, the Shields number indicates mobility. The higher it is, the more mobile the sediment is, but the precise lines do depend on grain size. To familiarize yourself with the grain sizes we are talking about, we have no motion, bed load plus suspended load. In this range, we are looking at coarse gravel or cobble rivers. In this range, fine to medium gravel rivers. In this range, coarse sandbed rivers. In this range, fine to medium sandbed rivers. And in this range, rivers with a bed of silt. What do these rivers look like? Well, let's begin with our coarse gravel to cobble rivers. This is a beautiful example, to me anyway, of the Waimakariri River in New Zealand, which is a classical coarse gravel bed stream. So in this range, we are looking at streams like this. Or closer to home, I'm almost positive this is a Rio Ara, but if somebody knows, they can correct me, but this certainly is a river in the Pyrenees in Spain, which is a classic gravel to cobble bed river. Now we move to fine to medium gravel bed rivers. Again, 2 to 25 millimeters. A very famous and characteristic stream in that range is the Hi River in Japan. Many of these rivers flow from regions of weathered granite, which is particularly suitable for the formation of material in the small gravel size. Now we move to coarse sandbed rivers. Sediment transport is mostly bed load. Well, most of these streams have dominant suspended load, but this suspended load is wash load. It's moving through the system without interacting with the bed. The bed material in these streams is moving somewhat in suspension, but bed load tends to be more dominant. And the Wabash River, which I showed you earlier, is a nice example of a stream that fits in this range. Beautiful, actively migrating river, which is not too far from where I live. If we go to fine to medium sandbed rivers, I have divided them into a non-tropical group, and in the red, a tropical group. And the tropical group includes some of the largest rivers in the world, and all big tropical rivers seem to be in the fine to medium sandbed range. There are many examples I can cite, but this particular one is on the border of Illinois, and I live in Illinois, so it's nice to show it. This is the Mississippi River, not too far from St. Louis, and if you look, you can actually see some navigation on the river. Finally, we go to siltbed rivers. These are not particularly common, but if we look, we can find them. For example, the Yellow River in China is a siltbed river. The particular example I've chosen here is the Bermejo River in Argentina, which has a bed of about 40 microns, and it's flowing into the Paraguay River here, and you can see the huge difference in suspended sediment concentration. It moves in, it's worked down by an eddy, comes up again, and you can see the dramatic effect it has on the suspended load of the Paraguay River. So this shows the full range of rivers that we have, ranging from the gravel bed, the coarse gravel bed cobble range, all the way up to fine to medium sand and siltbed rivers, where we have dominant of bed load, mixed bed load, suspended load, and dominant suspended load of the bed material. Again, the streams may have more suspended load than bed load because they are moving very fine material that does not interact with the bed. But this is based on the material that interacts with the bed. Okay, I'm going to talk about scour around bridge piers, a very popular topic with civil engineers. The particular example I show here is from the Skeiðará Sandur in Iceland. In 1996, there was a volcanic eruption underneath a huge glacier, creating an event called a Jökulhlaup. I believe the peak flows were 30 to 40,000 cubic meters per second, melting ice under the glacier and a huge outflow. And this caused huge amount of damage to the infrastructure in Iceland. This shows one single branch of the Skeiðarársandur is a very wide braided stream. This shows one branch with damaged piers. And those of you who know about bridge scour will be familiar with images like this. And you'll say, yes, you can get scour there. But that's not what I'm going to talk about. I'm going to talk about a hidden case, which is the bridge scour that results around large sandbed rivers, which you can never see because the bridge piers are deep and the river is perennial, covered with water, so it's very, very hard to see what is going on. The particular examples here are from the Mississippi River. This is further south than Illinois, but it shows some images of bridges where we must design for scour in a deep sandbed river. Now, quite a few years ago now, we did a study in which we specifically tried to look at the conditions that correspond to what a river like the Mississippi would do in a flood like a Bankfull flow. And this shows the channel we used. It's about 9 meters wide. We could recirculate the sediment, which is about 0.5, 0.6 millimeter sand. And we could place a circular bridge pier and a rectangular bridge pier in them, and we purposely made them of clear plastic so we could film the flow event looking upstream from inside the pier. We used the diagram that I'm showing here specifically to design the flows so that the range that would be covered from a small flood to a medium to a large flood event would fit within the range of flood flows in sandbed rivers such as the Mississippi. So our points are designed to fit within the cloud of these streams. So there's our data. Now, I'm going to show you a video clip. It's a little bit long, so I may abbreviate it, but I believe it illustrates some things that have not normally been seen by people about sediment transport under very, very violent and strong conditions associated with floods. Now, we used two flumes, the large flume I showed you, 3 meters wide, and another smaller flume, 1 meter wide. But in both cases, we tried to model flood flows. This is the smaller of the flumes, and this shows the scour process as we slowly increase the flow from a value too low to move sediment to one corresponding to a flood flow. I apologize, the units on the scale are inches, and what can I say? There are 2.54 centimeters in an inch, and this work was funded by the National Highway Administration in the United States, which does not recognize the existence of the System International. As the flow velocity increases, you will see sediment transport events which we do not normally associate with standard rectilinear flow. You will see sediment pulled out by eddies. You will see a repeatedly collapsing face. This now is in our main channel against a circular pier. Run 3 is our second highest flow. So this is not the most violent flow, but this is the kind of conditions that we are looking at during a flood in a large sandbed stream. And as far as I know, there is no standard sediment transport relation that has any hope of predicting this. There are 3 factors that make it different. One is the pressure field is strongly non-hydrostatic, and our standard formulation for sediment transport is based on hydrostatic flow. And second, the flow contains a collapsing face that is higher than the angle of repose, and third, it contains large discrete eddies which can move sediment out of the system. This is our highest flow. And if you are an engineer who wishes to protect against scour, you have to protect against these kind of flow and sediment transport events. Again, you are looking upstream from the inside of the pier. Now you see an example with riprap, stones around the pier, and a geotextile underneath to help prevent the winnowing of sediment from the bottom. And what we found is that these particles tended to sink over time. Notice that the riprap particles are becoming unstable. In some cases, the riprap did not move, but it sank so low that it was no longer protecting the pier. It was not entrained into the flow, but it sank vertically. Now you see a geotextile underneath to help prevent the removal of sediment from the bottom. And one by one you can say goodbye to the riprap. So when riprap fails, this is probably what is happening in the field. And there goes the geotextile. Okay, the next topic I wish to discuss is also a topic that should be of interest to Catalonia in particular and Spain in general. It involves the consumptive use of water in a relatively arid mountain environment. I've shown an example here. This particular river is in Alberta, Canada, not the United States, but it illustrates a gravel bed river at low flow in which there's really not very much water to use, characteristic of the area around Barcelona and much of Spain. And the river during a 100-year flood, when there is a lot of water to use. And in areas like this, people like to use the water when it is available. So they like to extract floodwater flow for consumptive purposes. The particular rivers of interest here are in Idaho. The example I am showing here is the Salmon River, one of the rivers in our set. And the question is, how much floodwater can we remove from a hydrograph without creating damage? We ought to be able to move some water, but the question is, how much? The central issue here concerns the habitat of the river. The particular example I am showing here is salmon spawning in a stream. This particular stream is in Japan. But in general for fish in mountain rivers, sand is not good. Some people describe sand as a poison for mountain rivers that creates a substrate with a low hydraulic conductivity that moves rapidly and creates a bad environment for organisms living in the sand and the fish that eat those organisms. Now, all over the world, there is an attempt to try and restore rivers that have been damaged ecologically. And yesterday, I had the privilege to go with Juan Pedro to the Rio Besos here in Barcelona. And I was told that not so many years ago, the river was so polluted that there was no hope of seeing fish. But fish have returned to this stream now. Not perfect, but getting better. And this indicates one of the concerns that engineers must face. So the Idaho rivers in question are a subset of those coarse gravel and cobble rivers that I showed you earlier. This is where the reaches fit. We were studying what the effect of removing floodwater from a hydrograph is on the content of sand in the bed, with the idea that the higher flows are capable of keeping sand in suspension and functioning with a lower ambient concentration of sand in the bed. If we reduce all the floodwater flows, there's nothing to prevent the sand from depositing. So we built a 1:24 scale model, and you can see here some large stones which we used to model colluvium. Here is the gravel, and the white material is our model sand. We designed the model so that the Shields number would be in the middle of the range of what the Idaho rivers show. It's a 1:24 model, so the grain size must be scaled downward. However, through much of that range, the threshold for critical motion doesn't change much. So the dependence on grain size is probably not so large. So we have the right Shields number at flood flows, and we have made the grain size smaller, but not so small that it probably makes a big difference in the flow and sediment transport dynamics. We tested to see if our model was good by looking at a dimensionless water discharge using grain size, a dimensionless bankfull depth, and a dimensionless bankfull width. We took a subset of our gravel bed data from Idaho and 2 other locations and plotted dimensionless depth versus discharge. There's our experiment, a little bit on the low side, but within the scatter. Here's our dimensionless width in the right range. There's our slope in the right range. And based on this, we could say that we had a pretty good model of the processes that occur in the coarse gravel bed streams of Idaho. There's our model hydrograph. It is a scale model of a short, flashy hydrograph characteristic of steep mountain streams. We conducted several types of experiments. In one experiment, we simply held the discharge constant at bankfull flow all the time, where this shows our percentage of bankfull flow, and this is a measure of our sediment feed rate. Run 6 was our full hydrograph. Note what happens as we go to other runs. We start off by taking out this part of the hydrograph. In run 3, we cut down that part of the hydrograph. In run 4, we cut down more of the hydrograph without changing the sediment supply, because presumably people want to get the water, but they don't want the sediment. In run 5, all we've left is a single part of the peak flow and taken the rest of the water out. What effect does this have on the bed? You can tell what's happening by looking at grayscale. The fine model sand is a white coarse silt. The full hydrograph shows a very low sand content. The constant flow shows a much higher sand content. In these 3 images, you see the full hydrograph with not very much white space. Run 4, where a substantial part of the hydrograph was removed, more white space, and considerably more sand in the bed where we had the maximum amount of removal of flood flow. This diagram shows the percent fines in the surface and the substrate for each of the runs, constant flow, full hydrograph, and gradual removal of pieces of the hydrograph. And what we see is a gradual increase in the content of fine material in the bed from about 25% at the full hydrograph, a pretty typical value for a field gravel bed stream, about 25% sand in the bed, up to values up to nearly 45%, which would usually indicate ecological damage. And we hope information like this can tell us how much water we can remove and still maintain the habitat appropriate of fish in terms of the sand content. Okay, I move on to a third topic, which is land building in the Mississippi River Delta by large engineered diversions. By now, all of you are familiar with the Hurricane Katrina disaster. The past few years have seen a number of very terrible disasters. We had the earthquake and tsunami in Indonesia and the Indian Ocean. We had Hurricane Katrina after that. We had a very bad earthquake in China after that. We had the earthquake in Haiti after that, and now we have the terrible event in Japan. In the case of the Mississippi River Delta, the disaster was known in advance and could be predicted. No one can predict precisely when an earthquake would occur, but in this case, the risk to the Mississippi Delta and New Orleans had been increasing over time. This diagram shows rates of land loss. Here is New Orleans, here's the shoreline. We have the highest rates of land loss here. The Mississippi Delta is gradually sinking into the sea due to subsidence of the ground caused at least partially by the extraction of oil and natural gas, and also by sea level rise. And the result is the delta is gradually drowning. The river supplies sediment which could be used to counteract subsidence and sea level rise and build new land, but levees prevent that sediment from being delivered to the wetlands, and instead we prefer to export it in the general direction of Cuba. Perhaps the American military's goal is to bury Cuba in sediment from the Mississippi River, but they don't use it for land development. Now, most of the Mississippi River, the delta, is sinking into the sea. The river is completely leveed. It delivers its sediment right to the edge of the continental shelf in an area where it can do no possible good to build land. But there is a distributary known as the Atchafalaya River, which then has two more branches, which is actively and freely forming new land today in terms of the Atchafalaya Delta here and the Wax Lake Delta. Our goal was to use a morphodynamic model to try to understand how we could build land and how we could design engineered diversions of the Mississippi River to replace land south of New Orleans. I am not going to discuss the details of the morphodynamic model today. Instead, I tell you that we developed the model for an axially symmetric delta on the average, such as the Wax Lake Delta. We then tested it for the Wax Lake Delta because we know exactly when this delta started to form. In 1973, there was a dramatic flood on the Mississippi River, and that caused an avulsion, or a channel shift, of part of the Atchafalaya River into a navigation channel, the Wax Lake channel, and this captured about 40% of the Atchafalaya River's flow, and that sediment started to deposit. For about 7 years, the sediment mostly filled up a fairly deep zone before we reached the sea. But starting at about 1980, this delta gradually built seaward, and there is a very, very good record of what happened in terms of the rates of growth, in terms of the grain size distribution of the sediment, in terms of the flows. and the data that we need to test a morphodynamic model was available to us. This problem is not so special or unique that it's characteristic of the United States. There are endangered deltas all over the world, and perhaps your best example that I'm aware of here in this part of the world is the Ebro Delta. Now, our morphodynamic model for land building was based on a zone with a channel and a floodplain, followed by a radially symmetric zone which could have multiple channels that are able to build outward. We did not model the switching of the individual channels. We modeled a virtual channel, assuming that in time the sediment would spread out in an axially symmetric way. We developed a model for the Wax Lake and applied it to the lower Mississippi. Where do we fit in the scheme of things? That is the values of grain size, dimensionless grain size, and Bankfull Shields number that we used to model designed avulsions or diversions of the Mississippi River to build land. Now, again, I'm not going to go into the details of the model, but it's classic morphodynamics. We link hydraulics, including shallow water equations in axisymmetric coordinates, and a sediment transport relation, in this case the Anguland-Hansen relationship, which is appropriate for a large sandbed, for sandbed rivers in general. The image we see in 1974 is at a time when most of the sediment was filling this region here and had not started building out to sea. We have a more precise comparison with data showing the agreement of the model, but this should illustrate the point. This shows the delta in 1990. We don't precisely know what the sediment supply is, but we do know that between 25 and 38 million tons per year is a good bound for the suspended load. And within that range, we get the progradation reasonably good. This is in 2000, 2002, and 2005. And I am very proud to tell you that the parameters in the model have not been heavily calibrated. We were able to get independent values for most of the parameters from similar sites, which, because the sites were dynamically similar, turned out also to work reasonably well for this site. We then used that model to look at one possible plan for trying to partially restore the Mississippi Delta. This is only one of many plans that have been proposed. The city of New Orleans is here. This is the Birdfoot Delta right at the break of the continental shelf and slope. This particular case looks at two diversions into Barataria Bay and Breton Sound. We are assuming that these are engineered diversions with a proper diversion structure that can divide the flow appropriately, because there is still a need to maintain navigation on the Mississippi River. Our design condition is to divert 45% of the flood flows into Barataria Sound and Breton Bay. We have some assumptions in the model: 2 millimeters a year of sea level rise. That's only one example we did, though. We used values up till 10 millimeters per year. 5 millimeters per year of subsidence. Again, 45% fraction of water diverted. And we put in 5-kilometer guide channels. And after that, we assume the river does what it wants. If we were to implement this for this particular scheme, this shows an estimate of the delta geometry in 2020, 10 years after the start. 20, 30, out to about 100 years beyond 2010, 100 years beyond last year. In this case, we are able to build about 900 square kilometers of new land. we are only using 45% of the available sediment. We could get that number well above 2,000 square kilometers of land if we use all of the sediment in the Mississippi River plus all of the sediment in the Atchafalaya and Wax Lake channels. So we believe there's a substantial amount of sediment to build new land. There's a lot of debate because we know the sediment supply to the Mississippi River has been reduced substantially by dams upstream. As far as we know, the sediment supply today is about half of what it was 200 years ago. But that's still a large amount of sediment. It's about 210 million tons per year. And we believe you could use that effectively to build land. We also believe it's possible to use all the sediment because there is no real need to maintain navigation here. There is a pathway in New Orleans which goes upstream of this. It's called the Mr. Go channel. And that would allow ships to avoid this area. But there is a political problem. There is a union of pilots who pilot large ships up this region, and they would all lose their industry if the ships were to enter here. And they have, of course, political connections, like lots of people have political connections, and those political connections may make it difficult to use all of the sediment. Okay, I have one last talk to discuss. I'm only going to talk about it in a general sense. It's migration of meandering rivers, which has been of great interest to me since the beginning of my career. And I was involved in the very early days when we developed models of how rivers meandered. And in those models, we assumed that one bank would erode and had some relation for erosion, and the other bank would automatically follow and deposit so that you maintained a constant width as it eroded. And about 12 or 13 years ago, I became very disillusioned with that idea and looked around for a type of model where the eroding bank follows rules of local fluid mechanics and morphodynamics for erosion. The depositing bank follows its own rules, and they talk to each other to establish width. I won't go into details, but the type of model we have put together assumes that as we erode a bank, slump blocks of vegetated sediment fall in, protect the bank until they decay. We furthermore assume on the inner bank that vegetation tries to grow inward on the point bar, but that vegetation is restricted the larger the shear stress associated with flood flows are. We tested our model using Muddy Creek, Wyoming, a small stream, beautiful meandering stream in the United States. There is an interesting story here. There is a wooden scaffolding for velocity measurements, and one of the researchers doing these measurements thought that slump blocks of vegetated sediment that fell in were interfering with his instrument. So they removed all the slump blocks, and when they came back the next summer, the river had eroded half a meter, leaving their scaffolding sitting in the water. Where are we for this stream? Muddy Creek fits in the range of medium to coarse sandbed streams where there is some suspension of the bed material, but the dominant mode of transport is bedload transport, Now, I'll show you a video clip from work by one of my students. I have to run it. It doesn't run from PowerPoint. But we did a simple assumption of steady uniform bend flow, but we allowed the outer bank to erode according to outer bank laws with slump block decay, and the inner bank to deposit according to vegetal accretion. So you will see river width adjust as the stream meanders. So as the stream migrates, you can see that for a period, the inner bank and outer bank move at different speeds until we can equilibrate toward a roughly constant width. Now, we are working in close association with a colleague and friend of mine in Japan, Yasuyuki Shimizu, who lives and breathes morphodynamic modeling. And he recently sent me a video clip of the latest version of work that he is doing at his end, and it's so beautiful, in my opinion, that I can't resist showing it to you. It's a full morphodynamic model that does not impose constant width. Width adjusts naturally as the stream migrates, and I believe that it is the most realistic modeling of meandering that I have ever seen. This is not particularly to any scale, but I believe it illustrates the concept of a model where the river determines its own width as it migrates. Now, this is only in its early stages. It'll be a long time before we get a model that we're completely happy with. But this was enough when Shimizu-san sent me this video, enough to make me excited, sufficiently excited that I did not sleep very well that night. Okay, that's my talk. It has been a great pleasure to come to Barcelona, and of great interest to me to have wonderful conversations about science, about engineering, about politics, about Catalonia versus Spain, and other interesting topics. Yesterday we went to the Susqueda Dam and had a most interesting trip. And of course, we were all very happy that Carlos had successfully defended his PhD thesis. Now we have to see that those papers get written. And it was also a great pleasure to go to the Rio Besos and have a view of what people here at the university are doing to try and rehabilitate the urban fluvial environment. And so again, my thanks to Juan Pedro and also to Alan for your wonderful hospitality. And thank you for listening to me for so long.
Ok, ahora queríamos que hubiera preguntas y mi papel es el de promover ahora un poquito de debate, y me parece que ha habido tantos temas y yo he tomado nota de varias cosas, y creo que personas tan cualificadas como muchos de los que están por aquí pueden tener curiosidades o ampliaciones o discusión de algunos aspectos. Y en ese sentido, para favorecer todo eso, yo trataría de traducir al inglés las preguntas, si lo prefieren así, del castellano o del catalán, de manera que este es el momento de hacer preguntas a Gary Parker. Así que es el instante del silencio, ese instante un poquito mágico del silencio en el que cada uno puede sentir un poquito dentro la responsabilidad de intervenir. Y hay muchas personas que pueden decir cosas muy interesantes, también aportaciones. En ese sentido les digo cosas que yo he anotado, things that I wrote down from your presentation to promote discussion. Just an overview of what we have seen today, the classification of rivers, the type of bedload and sediment, suspended sediment load, the scouring in Bridge Piers, a very nice topic on geotextiles. I think that's one of my questions. If I have time, I prefer you to ask rather than me. Geotextiles in riprap protections. The topic on sand is a poison, you said. The way sand are filling the gaps in gravel bed rivers and it's a damage for fish spawning. Then the delta formation, the land building, we saw the Ebro Delta too. Physical modeling was a methodology in your speech, numerical modeling too. This opens a large number of questions on the limits of these two methods. I would like to ask you also, but first you should ask first than me. I'm just the person to promote discussion. The levees, las motas, the levees in the case of Mississippi River, have you seen how these levees produce some problems? And that's an overview of the things we have seen, numerical modeling at the end on meandering rivers. Anyone, please, I move through the room to give you the microphone to ask questions in Spanish, in Catalan, or in English, doesn't matter. I will try to translate, or someone can help me, someone who is more fluent than me on English can help me to translate. Then it's your time, Jose.
Sorry, like you, I am also an old man, and not an engineer, I'm just a biologist. And there is a long time when you start a project on a river. I don't work with laboratory models, and my question is, what can we do? Because I have the feel of losing years and years on maybe with things, dispositives like score chains, or what kind of device could we use other than aerial photographs just to study the movements and the real bed loads on the rivers? Maybe there are easy systems. I remember the old one, the typical score chains, you know, things like that. Are they useful?
Well, of course, sometimes. Oh, you want to translate the question? I'm sorry.
No, the scour chains. The scour chains.
Old technology is often very good technology. Leopold chains, as they are called, are very simple to install, and they give a very nice measurement of maximum scour depth. And so they are useful today, and they will remain useful for the foreseeable future. Another older technique that has now been revitalized is to put marked stones in the bed in a column and observe how they are removed and where they go. And this has been revolutionized by the use of, in English we call them RFIDs, the kind of little tags they put on your clothes at the store so you cannot steal them, so that when stones have moved we can recover them and find out where they go. And these are being, so it's basically an electromagnetic means to track particles, and these are proving extremely valuable in tracking where particles go. And if we know where the particles came from and where they go and how long the flood lasted, we can back calculate bedload transport rates from that. Perhaps the most exciting thing today concerns acoustic methods, which look at particles striking some kind of object which then can give a sonic signal. These have been tested for probably some 40 years. They have been tested and they have almost always been found lacking, and one of the biggest problems is they have trouble distinguishing between a small sediment transport rate of big stones and a large transport rate of small stones. But technology has advanced to the point where I believe there are now a number of useful technologies that can be used using acoustic measurements of collision, which can now give us better estimates of bedload transport. There are other old-fashioned ways that work. Dig a big pit and measure how long it takes to fill it. So between the old ways and the new ways, I believe that measuring bedload transport is not nearly as difficult as it used to be. Doesn't make it easy, but...
First, thank you very much for this beautiful and inspiring talk that I enjoyed. And I have a small question about the model you presented a model on land building.
Yes.
For deltas. Is there some influence of wave activity or just river dynamics?
In the particular case of the delta that we're looking at, which is the environment that we're looking at, which is the northern shore of the Gulf of Mexico, the tidal environment is microtidal. And the information we have about hurricanes and storms suggests that they do not play a major role in deforming the delta shape, which is evidenced by the axially symmetric shape of the Wax Lake and Atchafalaya deltas. So we seem to be working in an environment there where we can certainly neglect tides. It's a 30 centimeter amplitude. And that storms are not playing a big role in shaping the delta. We move to a different environment and everything changes. I mentioned to you that I am trying to follow your lead and late in my life become involved in in coastal and tidal morphodynamics. And one case I am trying to learn about is the Bay of Fundy in Canada, where there is a 7 to 15 meter tidal range. There is no delta in the classic sense there, because if sediment deposits to form a delta, the tides simply completely redistribute it and take the shape away. So we can imagine a range of conditions, as of course the standard terminology is tide dominated, fluvial dominated, and wave dominated. Things are, as you know, rather more complicated than that simple triangle. But the type of delta we are looking at is only one member of a range of forms that, in my opinion, are stunningly beautiful and are the kind of things that, simply in terms of their intrinsic beauty, keep people like you, Albert, interested in working in the coastal field.
Thank you.
Más preguntas en cualquier lengua. Hay dos ya. Muy bien.
Thank you very much for coming, and the organizers. It was a fantastic presentation. My name is Jordi, and I'm a PhD student in urban planning, studying the Urbana River in collaboration with Catalan Water Research Institute in Girona. And since I study the Llobregat, I'd be interested in knowing, so excuse me for the very basic question, but where the Llobregat, or maybe the Besòs, if you're more familiar with it, where that fits in that graph that you showed. I wonder if it's constant throughout the watershed. Maybe it migrates as a Pyrenees, starts off in the Pyrenees as one type and then moves into a different type of river. And then my second question is how restoration actions or measures would vary across that gradient from silt rivers to coarse rivers. Are there restoration measures that are similar across all those rivers, or are there differences? So thank you for the non-expert question. I'd appreciate it.
I can tell to you that this river is 20 millimeters grain size.
Okay.
And Llobregat is something like that, or a little lower than that.
I think I have understood the sense of your questions, and I have two comments. One is not completely justified, but it's still my comment. I believe there is one technique for river restoration that will work across scales, that if you have a chance to implement it, you can make it work in the same way for siltbed rivers, sandbed rivers, gravelbed rivers, and that is for human beings to get out of the way and let the stream do what it wants. And when this has happened, streams are quite resilient. They are almost like living organisms. They make their own decisions, and they can often repair themselves nicely. And if you want my favorite example, is that there are companies these days that design restored channels with beautiful meanderings. And one flood later, often, because the river decides, well, I want to meander, but not particularly that way. However, my comments are too strong, because, for example, if we take the Bankfull River here in town, it's not, we simply cannot say, let's make 200,000 people move away and let the river do what we want, what it wants. And under those circumstances, of course, the techniques have to be quite, I think, substantially different from case to case. What you would do for a gravel or a cobble bed river will often be oriented toward maintenance of in-stream habitat for fish and other organisms. And I am not an ecologist, so you know more than I do, or a water manager. But when we are looking at the larger sandbed streams, it turns out that from an ecological point of view, restoration of the floodplain is as important as restoration of the river, because often floodplains play a very important role in aquatic habitat during floods. They provide refuge for fish, they provide spawning areas, and they provide other features which are characteristic of rivers that have very long decays on their hydrograph. Mountain rivers go up and they go down. And so the residence time on the floodplain is not long. Lower, larger sandbed rivers usually have flows that have substantial residence times on their floodplain, and therefore what happens on the floodplain is equally important as to what you do in the channel itself. Also, there is the standard issue of scale. In the smaller gravel bed rivers, you can enter the stream, bring a bulldozer, move sediment around, put stones in it, arrange things, try and create riffles. And if you are looking at a stream the size of the Wabash River, which also has, to a certain extent, a damaged ecology, none of that is going to work. And if you wanted to do something to try and improve the stream, doing something about nitrate inflow might be a lot better than trying to build various kinds of structures on the stream. So I would think that I'm not an expert on all, I know a little bit about a little bit, but I wouldn't think that if we have to intervene in a substantial way, that the way of intervening would be universal across the scales.
Well, good morning. I'm Albert Herrero, and I'm a PhD student with Professor Allen Bateman. And well, my question was about the delta land building model, and about the hypothesis you do about the evolution in the following 100 years about the sediment discharge. Because I guess that even social aspects and, well, many things have influence in this evolution.
You're absolutely right. The unfortunate byproduct of a democracy is, since that everyone has a voice and everyone can have an opposing voice, there can be a pull this way and a pull that way, and the result is that nothing happens. People tend to think in a very narrow way, not because they are narrow-minded in many cases, but because they have to live month by month. And one of the problems is just a sample problem with delta restoration is oysters. Area that once was freshwater habitat has now become brackish, somewhat salty. And that has made it appropriate for oyster farming. So now many people who earned their livelihood in a different way now have become oyster farmers. Now, if you build new land, you push seaward the zone of freshwater and bury areas that are being used for oysters. And a lot of the people say, no, we don't want this, this is bad. And they will even say it's environmentally damaging. Now, it is not necessarily because they are narrow-minded. It's because they have a house, and they have a car, and they have their children's education, and they may see the broader picture that in the long term this might be good for the delta, but they have to pay for the car every month, and they have to pay for the house every month, and they have to send their children to school. So at the small scale, to them, it's a disaster. And likewise, we have a petrochemical industry, we have a navigation industry, we have urban interests, we have all kinds of counteracting interests. Our goal for this plan was to put something in front of everyone that we thought had a sound scientific basis. And we believe this is the first model of land building that was based on a proper morphodynamic model. Okay, now, the social aspect, here's a model. We can change the point of introduction of sediment. We can change the amount of diversion. We can make 3 or 4 or 5 smaller diversions instead of 2. We have the flexibility to model all of these things. Now, as a society, other people with other considerations have to provide social and economic input. But we hope that we've provided some rational basis for doing that, because at least now they have a model to talk about. And before, there were people who would say building any kind of land is impossible. And one statement I heard commonly is the Mississippi River doesn't have enough sediment to build land, so you can't do it. And I think we have been able to demonstrate that that is not true. So I hope we have put the first step of a long series of steps that will require substantial social and economic input, which we cannot provide.
More questions in any language? I can see people that knows a lot about these topics.
Bueno, sí. Aviam, tots sabeu que hi ha la pressió urbanística ha fet reduir moltes vegades l'amplada i la capacitat dels rius quan passen per ciutats, no? Llavors, una de les solucions que es proposen a vegades és fer una bassa de laminació aigües amunt. Clar, això té una influència directa amb el transport de sediments i li volia preguntar si allà en fan o com veu o si a priori considera una solució a estudiar. Clar, depèn, hi ha rius que porten més sediments i en canvi n'hi ha que estan en equilibri o que inclús estan estan perdent sediments, no? Per tant, no totes les respostes seran iguals, però si d'entrada, no sé l'experiència que pugui tenir el professor.
Algú pot ajudar? Balsa de l'eliminació, diríem retention tank. Retention tank is in urban environments, but basin, rotation basin. He's asking about urban rivers where the channel is encroached by the city, like in Bankfull River. And in this country, we are very used. We have doing some building some retention basins in the basin for lamination, for laminación, to reduce the peak flow, And he's also concerned about the sediment in this case. If the sediment will be through the river, still through the river, or some effects can come in the river. In case of retention basins to abate the peak flow. Then we build retention basins which are not impoundments themselves, but to abate the peak flow. And what's the effects in terms of morphodynamics? That's the point. We are doing this very much.
Okay, yeah. Of course, I'm not really sure that I know all the answers, or even half the answers. The first comment is that if you divert water, you're going to divert sediment. And it's very, very hard to divert water, but not sediment. If you can take the water from relatively high up, then you're collecting finer sediment. But the fundamental way that rivers develop their floodplains is through overbank deposition of sediment. So it's a natural process. I imagine that if your retention basin allows flow out of the basin as the flood declines, rather than permanently impounding it, you could limit the amount of deposition. I would guess over time your retention basin will fill with sediment, and it may be necessary to dredge to maintain it. But with an appropriate design and with an appropriate knowledge of the sediment supply, it may be possible to keep them alive for many decades, I hope. Retention basins actually are a engineering model of a nice natural phenomenon, because large rivers with floodplains substantially damp their hydrographs by putting water on the floodplain. And then that water later on flows into the stream itself. And part of the reason that on large rivers the hydrograph tends to decline so slowly is because of exchange of water between the channel and the floodplain. So the use of that engineering technique actually is a good model of how nature organizes itself. So it's a sensible design in general, but sedimentation is not going to be stopped. Maybe we can reduce it.
Sí, hola. Mira, la meva pregunta jo la faré en català i és la següent. En el moment en què estem parlant de guanyar terreny al mar i utilitzem la càrrega del riu per redistribuir-la pel delta per guanyar en algunes zones del delta terreny al mar, aquesta càrrega a la zona del prodelta, que no hi arribarà, afecta d'alguna manera? Allí es deixarà de guanyar terreny o es perdrà? O quina experiència té el senyor Parker?
Yes, the question is on the land building. When you divert sediment for land building, like in the case in Mississippi, this sediment is lacking in the pro-delta, in the prograding delta. And he's concerned that this prograding delta may suffer some effects of the sediment diverted upstream. And is your experience that it's not a problem, or it is?
Yeah, I don't know if I can find it quickly, but I can try. Let's see. Unfortunately, I cannot find the best image. This will illustrate, however, at least part of the issue here. This illustrates the other half of me, which is down below the surface of the sea. Here we have New Orleans is about here. Here's our shoreline. This is the continental shelf. At about 200 meters, we move to the continental slope and down into deep water over 2,000 meters deep. And there is the present-day delta of the Mississippi River. This diagram is not as good as I would like. At a finer resolution, you will see that the Mississippi Delta has built all the way out the shelf slope break. There is nowhere for it to go. Where it is located now, it simply cannot prograde because it moves into very deep water very rapidly. So this delta is not prograding today and has not been prograding at least for the last 300 or 400 years. It's stopped there. It cannot go further. And this again underlines the condition that sediment delivered to this location is being thrown away. It is being tossed away because it cannot possibly contribute to any land building. So the removal of sediment upstream can only have a benefit in terms of the use of the sediment to build land. There's no penalty you pay down here. Does that answer the question?
Well, it's a pleasure to be here, but also if we are learning a lot here, I have something like a worrying, especially when you said that example on the measured devices that get lost because they put away the vegetation. Which I would like to know, because it's very important here, because we have very changeable vegetation on river streams, which can be the change of the model if we consider that vegetation that is also changing all the time, and how does this affect to the general results of the models? You understand me? Yeah.
I understand you, I think, 100%. And the reason I believe I understand you 100% is because this is a critical issue that has not been addressed significantly yet. Especially on river floodplains, the sediment processes that create most river floodplains involve an intimate and close interaction between vegetation and sediment. One of my colleagues, Alan Howard, spent many years looking for a fully meandering alluvial stream that was not influenced by vegetation. And he found two, just two. And in that case, the replacement for vegetation was a kind of salt that could harden and then redissolve, which played the role of vegetation capturing sediment and being eroded. I don't have a precise answer to your question, except to say that I sincerely hope that if I can live 10 years more, I will see substantial new progress on modeling the interaction of vegetation and sedimentation. To give you a perspective for the problem we are looking at here, our model assumes that as we build land in the Mississippi Delta, that the deposit will consist of 1/2 sand and 1/2 mud. But in order to achieve 1/2 mud, vegetation is absolutely critical because mud won't deposit otherwise. But there's a second benefit. If you can get the vegetation established, it turns out that in deltas like this, you create organic sediment. And so the actual ratio would be 40% sand, 40% mud, and 20% organic sediment. Peats. And the more organic sediment you create, the more land you can create. And again, there you see the critical interaction between vegetation and sedimentation processes. All I can tell you is that there is a lot that we don't know, but there are a lot of ideas, and I believe it is one of the exciting areas in morphodynamics and sediment transport of rivers that is being explored today.
Hi, Ari. As you know, I'm a marine geologist, and since you put a picture of the Gulf of Mexico, I have a question about how different are meandering channels in rivers compared to meandering channels in deep sea funds. So they work in the same way, they follow different rules, and since you're working in both environments, maybe you are the best person to ask that question. Thank you.
For everyone else's sake, maybe it's appropriate to show an image or two. These are images from the deep sea. This is a meandering channel on the Indus submarine fan, a meandering channel on the Amazon submarine, on the Mississippi submarine fan, and meandering channels on the Amazon submarine fan. And this is another view of part of the meandering channel on the Amazon submarine fan. If you really like meandering channels, and if you like big ones, forget about rivers. Rivers are trivial. The largest meandering channels in the world are at the bottom of the ocean. And we are talking about channels with a width of up to 5 or 6 kilometers and depths of well over 100 meters. And the channels themselves can run for hundreds, or in the case of the Bengal fan, thousands of kilometers. So if you really like big meanders, forget about rivers, go under the sea. there is a very, very clear similarity in plan form, and that similarity can only mean that a substantial part of the dynamics, morphodynamics of submarine meandering is very, very similar to that of rivers. And there is a fundamental difference. I showed you natural levees on the Fly River in Papua New Guinea. The river was about 12 meters deep, and the levees were about 2 meters high. In the submarine environment, the river might be 40 meters deep, and the levees might be 150 meters high. And in cross-section, they are dramatically different. And that dramatic difference is governed by the fact that water is 1,000 times denser than air, whereas sediment-laden water from a turbidity current might be 1 or 2% denser than the ambient water, which means the cross-section looks dramatically different and is governed by different processes. The plan form appears to be quite similar. So I would say that something like about 60 to 65% of what we know about rivers is transferable to deep-sea submarine meandering, but another 35 to 40% is undoubtedly different and has to be considered in a very different way. It's my estimate.
Some more questions. We have time for questions.
If our hydrographic net is majority of more of 5% of slope, and our rivers are very energetic rivers, which is the challenge or the recommendation that you can explain us to try to doing a first approach to these rivers, to this kind of rivers, because more of 90% of our rivers have this kind of, are not alluvial rivers, are torrential rivers.
Yes.
And the issues that we can use to make the first approach to see how they can move or what they can transport. It's incredible, the rates that we see in the rivers.
Yes.
What should we do?
To solve what problem?
Steep slope. To solve steep slope rivers. Steep sloped rivers, more than 5% slope.
1 to 5% slope?
Yes, more than 5% slope.
Up to 5% is a little bit high, but to a somewhat lower slope, but also a steep river, I suggest you talk to Carlos and Juan Pedro, because Carlos' thesis addresses these issues with a very nice morphodynamic model of the effect of gravel mining on river profiles. And the particular model they have developed can be used to design various rates of gravel extraction at various locations and test what the response of the river is in order to try and find allowable amounts of sediment removal. If you move up to 5%, other things happen, which I found yesterday. I was taken to a wonderful trip to the Susqueira Dam. I am also interested in bedrock rivers at high slopes in the mountains. And I am trying to work these days on meandering of bedrock rivers. These rivers have some cover of alluviation on them, but shallow underneath is bedrock. But we don't know what the bedrock looks like. Well, yesterday I had a wonderful experience because the power plant for Susqueira Dam is located downstream of the dam, but not too far. The dam has blocked all the supply of sediment, so the alluvial cover has been removed, and we see the bedrock right there. And it was a very nice thing to see. When you are looking at slopes in the order of 5%, I would guess that most of the streams that you are looking at have bedrock not very far down. And in considering how the stream would respond to changes, rather than considering infinite degradation at a slope of 5%, probably you want to look at when the bedrock gets exposed and how that would change things. That would be my guess for 5% slopes. It's very difficult to maintain a completely alluviated gravel bed river at a 5% slope.
More questions?
Sorry, close to Susqueda Dam, down the water, there has been a dramatic change during the 50 years after the building of the dam, as the annual peaks of discharge have disappeared. There has been a big score of the bottom of the river, in some places around 4 meters, and there is a huge, I would say, sexual problem about the poplars, about the trees, because there is no possibility of reproduction by seeds. But by the way, there is a huge accumulation of trees in a place who used to be for the common 1 year, 2 year, 5 year period discharge. So there is a flooding problem also, a risk. Which one could be the best way, because we have no water, we are Africans on this way. I think probably is it possible to make a mechanistic with bulldozers intervention just to modify or make younger the shape of the river, just to not only a very narrow channel and profound one.
Wait on adding sediment to the river. The Germans and French people are doing this.
Adding sediment is one approach. In Japan now, they have a rather interesting practice, which I guess in some way is uniquely Japanese. They are trying to catch the sediment upstream of the dam and truck it downstream and dump it into the river continuously. And from an economic point of view, that kind of thing is affordable only in a country with a very high population density. But if there are available sources of sediment, then feeding sediment can help. The best thing you can do about the encroachment vegetation is to allow some kind of flood releases on a periodic basis. And again, it's this issue of interaction of vegetation and sediment transport. Rivers adjust so they can fight back against vegetation, which would close the channel. And there is a balance between vegetation encroachment and removal by the power of the flow itself. We take away that power, and now we see a vegetation morphodynamic narrowing of the channels. So restoring at least some of the flood peak is the best way to deal with that. I don't know if it'll work in this part of Spain because of your very severe water shortage, but I do know that, or I have been told that last week there was water flowing over the spillway of the Susqueda Dam. And if there is any way to design flood flows, even if they are much shorter than they used to be, that have velocities that are high enough that they mimic the conditions before the dam was placed, I think you can use that as one way to control vegetation. Otherwise, in countries like New Zealand, they are using machinery to remove the vegetation. And again, you could do that. I would prefer to look at something more natural, but...
Hello, I would like to ask you about the use of geotextiles and the ripraps and the protections of the river sites with something not only geotextile, but mantas de fibra de coco. I don't know how it's to translate. The coco fiber. Yes. And about the protection of textiles of different kinds.
Your opinion on the way of protecting banks, river banks, with flexible materials like coconut sheets?
I give you an opinion which is only based on a few cases that I have seen. And as far as I know, the use of things like coconut fiber should be successful only if it promotes vegetation growth, and then vegetation takes over the role of that. So if it is used as a temporary measure, which then allows vegetation to recover and take over the job of protecting that, it can be successful. But the coconut fiber itself, a good flood can just take it away. I have seen a number of examples where all of this was placed on a river very nicely, and then the first flood comes and there is coconut fiber there and there, there and there. But if it is considered as the substrate to promote vegetation, I think it can be useful.
Some more questions. It's time, still time for questions.
Hello, morning. I have a question about the PL score. You present a model results on to understand how the river scored the PL. But what about field measurement of this kind of sandbed river? You mentioned that it is not possible to see what is happening, and so the model give us a vision. So what do you think, or do you know have some experience on field measurements of this kind of phenomena?
It's impossible to be an expert on everything. And also, I am very clumsy. And so I am not fundamentally a field researcher, but what I do is I go with my friends. And then I try and help, carry this and carry that. And in that regard, I think the interesting development has been the application of technology originally developed for oceanographic applications, acoustic means of measuring the bed, that are now being applied to rivers. And it's interesting that the deep sea in many ways is easier than rivers, because when you are taking seismic profiles or acoustic profiles of the bed of the ocean, you don't have to worry about a big tree floating straight at you to destroy your instrument. And especially big trees, as we saw for the below the Susquehanna Dam, love floods. I do have a number of colleagues who are trying to work around debris, severe velocity fields around bridge piers, to use the acoustic devices that have been developed for oceanographic applications to measure the development of scour holes. And there is now a lot of successful data on that. What they can do is measure the development of the geometry of the scour hole, and this is very useful information because we don't know when the scour depth is peak. It's not necessarily when the flow is strongest. They cannot, at this point, however, measure the mechanisms of sediment transport. And this, as far as I know, is not yet possible in the field. So for the mechanisms, I think the laboratory work will be helpful, especially in telling us how we have to change our existing sediment transport models. Because our existing sediment transport models are not designed for the type of flow conditions we see during floods. Eventually, we would like to be able to have a physically based model which we could run numerically to predict these things, but I don't think we're going to get that from anywhere other than careful experimentation to understand the phenomenon.
Professor Parker, nice to meet you. You show us a picture of the Delta del Ebro River. And do you think that it's possible to do any actuation in order for the land building? And another question is, do you think that the climatic change will affect the main behavior of the morphodynamics of the river? Thank you.
Yes.
About the Ebro.
I showed the example of the Ebro River because I have always recognized it as a very beautiful delta, and I have known for a long time that in many senses it is an endangered delta. But I don't know enough about the details to feel confident to make a precise recommendation. I do think that much of our existing technology concerning deltas is probably applicable to the Ebro, but I would hesitate to come from the United States to your country whatever that country may be, and tell you what you should do with your river. I would say that I would love to work on the Ebro Delta.
What about flushing of reservoirs, flushing of sediment in reservoirs? You think that's a good solution to rebuild deltas?
Well, I give you a perspective that is not the local perspective here, but most of the basin of the Mississippi River has a low slope. The sediment is sourced mostly in zones of higher slope, the Rocky Mountains, but most of the basin has very low slopes. And therefore, the dams in the Mississippi Basin are not very high. And the typical dam in that basin now is between 1/3 to 1/2 full of sediment. And one by one, these dams are going to become completely filled with sediment within, not my lifetime, but many of them will be filled within the lifetime of people here. And what that means is within a slightly long engineering time, that sediment that was lost to the Mississippi River by dams is going to be returned, because nobody knows what to do with a dam that's filled with sediment. The situation, of course, is quite different here in Spain, because in steeper environments, you can often maintain reservoirs for much longer times. Sluicing of sediment from reservoirs actually is a topic that involves turbidity currents, and since I like turbidity currents in the ocean and reservoirs, I know something about it. And the key feature here is that you can use sluicing to get rid of part of the fine end of your sediment load. The coarse end stays upstream in the delta, and the delta progrades down, and as far as I know, no one has ever found a mechanism to successfully sluice that material out. So it can be a partial solution.
Thank you, Professor Parker, for your conference. I have a question that maybe it's on the other end of typical morphodynamics interest. You've talked somewhat about reductions in sediment transfer because of dams. But I was wondering, from the land development point of view, when we build cities, we are worried about the increase in outflow. When we do some work in the field and in the agricultural areas, we're worried not to increase the sediment production. Is there, to your knowledge, any documented cases in which there has been trouble generated in the river because we don't, because we don't take into account the reduction of sediment production because of urban processes, or because we tend to take too much care in not producing additional sediment in agricultural land?
This is a complicated question where the answer can go both ways. In the case of the Mississippi Delta, there is very clear evidence that there has been a reduction of sediment supply. And the evidence we have, at least in the United States, is there was a period when agricultural practices caused a dramatic increase of sediment. But over time, agricultural practices improved, and now the contribution, the direct runoff from fields, is not nearly as large as it used to be. In that sense, agricultural practices have caused an increase in sediment supply, but then it has been decreased above that peak. The end result, when all processes are combined, is that down in the Mississippi Delta we are seeing a reduction of sediment supply. But the dams and lakes upstream are capturing sediment, and many of those areas have shown a dramatic increase in sediment delivery. And I am involved in a group which is trying to figure out why the sediment supply has increased. And everyone wants to say it's because of the farmers. They cultivate the fields and they cause extra sediment to come in, and that's why sediment supply to a certain lake called Lake Pepin in Minnesota has increased by a factor of 10. And I believe that. We did a study of it and found out that that's probably not true. Instead, probably what happened is they use pipes to drain the fields to remove water. And the pipes don't deliver much sediment with them, but they change the hydrograph sufficiently strongly that the river valley starts to incise and erode its valley walls, and that seems to be the source of the extra sediment. So it's actually fairly complex, and at least in my case, I thought I knew the answer, and I was wrong. Direct runoff from fields in that case was not how extra sediment was being generated. But the point is, of course, as it's generated, all of this extra sediment ends up in a big natural lake on the Mississippi River called Lake Pepin, and that captures the great majority of it, and so it's not being delivered downstream.
Then we haven't spent almost 2 hours, then the questions should be very short, and the last 2 questions, please. Last 2 questions. Short. The last one, at least.
Thank you, Gary, for the conference. It's very interesting, all the topics. But as Juan Pedro and me likes a lot the laboratory experiments and in morphodynamics in rivers and all these kind of things, I want you to say us what is really the importance of this kind of work in research, because all the people are engineers, we are researchers, and for me it's very interesting your point of view about experimental things in research, in advance of the knowledge, etc. What do you think about this kind of research, laboratory experiments?
Well, what can I say? Yesterday, we had a wonderful lunch, and on the lunch was a wonderful salad containing onions and pimiento, and I like onions and pimiento.
Escalivada.
And therefore, my opinion is they are socially very important, and we must do a lot to protect them because they have a significant role in society. So I admit a certain prejudice. I like experiments. And for me, it helps for me to see things happening with my eyes. And eyes are important. Rivers are beautiful because you can see them meander or braid with your eyes. And I am not a very good abstract thinker. So my brain is not good enough, and I am not abstract enough to do string theory or quantum mechanics. I mean, I can't imagine it. Experiments help me visualize processes that then helps me understand them, that then teaches me in a qualitative sense what are the questions I should be asking and how to solve problems, and in a quantitative sense, what kind of formulation do I need to get the information so I can improve the physical basis, which then can feed into either theory or numerical models that more properly capture what nature or what the natural system is actually doing. And for me, experiments are a kind of bridge that allows me to move between numerical modeling and field expression. The idea being is that if I have a numerical model, it may be difficult to test it in the field. But if it doesn't work against my experiments, then it probably has something wrong with it. So I look at it from that point of view. I will say that, as we all know, the traditional day of hydraulic models without sediment, building a model of a spillway, are mostly gone because we know enough to do that numerically. Sediment transport contains laws that are not very well known even today. Maybe someday, in 20 or 30 or 40 years, we won't need that much experimentation because we will have the answers that we need for good numerical models. And of course, that is the goal. But I do not expect to live long enough to see that. And in between, I expect to enjoy pimiento, onions, and experiments.
Thank you. Then, any other short question? Then I should thank again Gary for your presentation, the questions, the answer to the questions. I would like to give you an applause.
thank you for coming.
That's all.